Hello, this is Christopher Pohl. What I'm going to do today is go over a range of topics, which has already been announced. Here's a quick outline of what I'm going to talk about. First, a review of basic column options, and then I'm going to quickly explain how to use virtual column as a means of selecting a column, and then discuss column selection as it relates to sample characteristics. Then I'm going to review a series of new columns that were introduced in the last couple of years. And finally, I'm going to talk a bit about troubleshooting IC column problems. So to start with, the basic column options one always has to consider often when you buy your instrument, but certainly when you're choosing your column, is the column diameter itself. Nearly all ion chromatography columns are available in both 2 and 4 millimeter formats. All instruments except the ICS 900 are compatible with 2 millimeter columns. But it's important to remember the advantages of 2 millimeter columns are particularly evident when you're using RFIC mode, because the cartridges last much longer when you're using 2 millimeter columns. Another thing that's important if you're going to use a 2 millimeter column is proper cutting of connecting tubing and sample loop when you're using 2 millimeter columns. For 4 millimeter columns, that's not as important, but an improperly cut tube can make a big difference in the performance of a 2 millimeter column. And for that reason, we recommend using Viper fittings when you're using 2 millimeter columns, so you don't have to worry about the quality of the tubing cut. And the other thing to remember is that many of the consumables are designed to go with a specific column diameter. So if you're going to use a 2 millimeter column, you need to use a 2 millimeter suppressor, for example. There are many, but not all columns are also available in capillary format. But in that case, you're restricted to the ICS 4000 or the ICS 6000, or if you have some of the older ICS 5000s, they're also compatible with capillary mode. But to work in the capillary mode, you need a capillary pump and a capillary flow cell. You can't just operate in the capillary mode with a 6000 unless you have the right pump and flow cell. And also, we recommend use capillary tubing based on the Viper design for optimum performance. One thing that's different about RFIC mode for capillary is that the cartridge is designed to last not based on ion count, but by duration. So the cartridge lasts 18 months, and we recommend, if you're working in the capillary mode, that you don't turn the pump off. Just leave the pump running continuously. It uses very little eluent, so there's not a problem with leaving it running continuously. Then you don't have to worry about equilibration in the morning when you get into work. Now, a third very obvious option is column length. Unlike HPLC, most ion chromatography columns are 250 millimeter in length, but there are many that are available also in 150 millimeter lengths. Shorter columns have lower capacity, but they also provide better speed, while longer columns have higher capacity and provide better resolution of complex samples. We recommend against using guard columns for separations, although some people do use them for that purpose. It's mainly because our quality control parameters are not as stringent on guard columns, because they're intended to be used as a guard column and not as an analytical column. Now, when it comes to stationary phase, one important parameter is the particle size. Obviously, particle size results in improved efficiency, but the thing to remember is that there's a very strong relationship between particle size and pressure. So if you reduce the particle size by a factor of 2, you will increase the pressure by a factor of 4. At the same time, the improvement in resolution, if you reduce the particle size by a factor of 2, the resolution is only improved by the square root of 2. So you get about a 1.4-fold improvement in resolution if you cut the particle size by a factor of 2. So the gist of all that is that, you have to consider the pressure rating of your system, because you can't make huge changes in particle size without exceeding the pressure limit of your instrument. So when you're starting with a new method, one of the things that we recommend is you consider first the maximum pressure specification of the separation column, then consider the pressure associated with the guard, and add a safety margin of 20% to deal with pressure increases associated with particles in your sample. And if all of those added together exceed the pressure rating of your instrument, then you probably can't use that column on your instrument. Or you're going to need to use a lower flow rate, which will mean the analysis time will be longer. So when it comes to 4-micron particle size columns, they may not work on older instruments, but sometimes you can use the shorter small particle size columns on older instruments. So that's just a word to the wise that the manual may say, for example, you can't use a particular column except for on certain instruments, but in reality, if you look at the pressure ratings, it may be possible. Now, the next thing I wanted to show you, just in case you're not familiar with it, if you have Chameleon as your software package, it has built into it a tool called Virtual Column. And Virtual Column is very useful in helping you develop new methods. But another benefit of Virtual Column is you can use it to find the best column for your application. So just to quickly view this in case you're not familiar with it, if you click on the box that says Tools on a Chameleon, this is the Chameleon 7.3 view of Chameleon, then you'll see that there's an option called Virtual Column at the bottom of the pop-out that happens if you click on Tools. And then if you click on that, it opens this screen that says Virtual Column. Now at this stage, you don't really see anything other than this screen, but what you need to do next is select the ion you're after, your analyte category, anions, cations, or carbohydrates. So once you've selected one of those, in this case we're going to select anions, then you need to start selecting analytes. There's a long list of analytes, and I'm not going to scroll. Since this is a screen capture, you have to take my word for it, but there's about 150 different analytes on this list, including some rather uncommon anions. So once you've selected at least 2 analytes, then you will see on the screen that I'm pointing at, I don't know, the screen below lists a bunch of different columns, and you notice that some say gradient and some say isocratic. You can select any one of those from that list, and you also have an option to select either carbonate or hydroxide or just gradient or just isocratic, depending on what you're doing. So, but for now, we're not going to, what we're going to do is we're going to select the AS11HC column. Now, at this stage, we still don't see that other image disappeared, and we have a blank area on the screen. That's because we still need to select a few more things. One thing we need to do is select the temperature of we're going to use on the column. So I suggest you always start with the 30-degree one because that's almost always the preferred temperature for most columns. And now you can actually see a chromatogram. Now, I just, for convenience, selected acetate and acrylate anions because they were right next to one another in the peak table. Now, you see the view you see once you selected the temperature is the fastest analysis time within a certain concentration window that's pre-selected. So here, under these conditions, you see here the LU1 concentration that provides the chromatogram you see below. But you can also click on the image above and drag around the concentration to get different retention times. So if you have a more complicated chromatogram, you can adjust the separation by dragging around this bar once you click on the screen, the upper image. Now here you can see that green line up above is what it looks like after I moved the cursor a bit to a higher concentration so that the peaks are coming out faster. Now you can, just to show you a comparison, although not a very meaningful comparison, I switched to the AS19 column, and here you can see the AS19 column has a much larger separation gap between acetate and the void under the optimum conditions, but we can certainly speed up the analysis in the same way I just showed you. Here's the separation when I've increased the concentration, so the analysis time is around 5 minutes for acetate and acrylate. Now, when it comes to selecting columns in consideration to sample type, the way I like to think about it is it depends on the complexity of your sample first and foremost. So if you have a simple sample that only has 2 or 3 different major ions, or you're only interested in chloride and sulfate or something like that, and all the other ions are very low concentration, you don't really care about them, then you probably want to select a short low capacity column because that will give you the maximum analysis speed, and the columns will equilibrate fastest. On the other hand, if you have samples with a high range of sample concentrations, like maybe you want to detect perchlorate in drinking water, and the concentration of chloride is 10,000 times higher than perchlorate, then you need a high capacity column. And so you should look for columns that are in the upper end of the capacity range so you can inject the most demanding samples with minimum effects on your chromatography. Now, if you have samples that have a lot of different analytes, what you need is usually a combination of high capacity and high efficiency, which translates to needing a long, high efficiency column. So there, you want to look for the smallest particle size that your instrument can work with, and the longest column that's available in that format. And for trace analysis, because you care about sensitivity, that depends on whether or not you're dealing with kind of ultra-pure samples or complex environmental samples. For ultra-pure applications like in ultra-pure water in a semiconductor fab, you're better off using short, high-efficiency columns because short columns give taller peaks, and high-efficiency columns produce higher, taller peaks as well. So that will give you the maximum sensitivity, all other things considered. For trace analysis with a diverse range of concentrations, though, you need high capacity as well. So in that case, you need it's recommended you use the highest efficiency column you can get with the highest capacity so that you can tolerate a wide range of sample concentrations. And then for high throughput, it's sort of the same as for simple samples. You want a short column, but you want high efficiency as well so that you can make the analysis as fast as possible and still resolve all the peaks. Now, I'm going to switch gears and review a few new columns to give you an idea of what we've been working on in the last few years. I'm going to talk first about the S29. This is a new buffered stationary phase column that is designed for carbonate eluent, and then 3 anion exchange columns designed for specific applications in the separation of anions, and then a cation exchange column, which is the first column we've ever made with 3 different types of cation exchange sites, and then a new high-resolution carbohydrate column, which is designed for separating food sugars. Now, the AS29 column is unique in that the carbonate eluent itself is buffered, but sometimes if you have a sample that's highly acidic or highly basic, you get artifacts in the chromatogram if you're using like an AS23 or an AS9HC. And what we did in this column is we included a ion exchange site that has a buffering ion built into the site so that it's more tolerant of pH fluctuations in your sample. So here you see that the column is tolerant of high ionic strength samples. The peak shape is really unaffected for fluoride, nitrite, bromide, nitrate, and phosphate when we have a fairly high concentration of fluoride and sulfate. But more interesting is this sample, which has a lot of carbonate. It really has no effect on the peak shape to have a sample with a lot of carbonate. Of course, with carbonate eluent, it's difficult to see carbonate, but often with like an AS22 column, if there's a lot of carbonate, the nitrate peak will be distorted by the carbonate in your sample. And here you can see everything looks just fine. Now, going on to the AS30, the AS30 column is a column designed specifically for separation of oxyhalides in drinking water. Now, under these conditions, which is the conditions we use to test the column in manufacturing, the analysis time is pretty long, but don't worry about that. That's not the operating analysis time, but that gives you an idea of what the separation is like. This column is the highest capacity column we've made in this hyperbranched chemistry, and which is reflected in this analysis time under isocratic conditions. But this column is designed for gradient applications. So if we look at it under gradient conditions, you can see why this is basically an improved version of the S19 column. It has a similar analysis time, but it deals with a couple of problems the AS19 has. One is, if you look at peak 1 in the chromatogram, that is an artifact. If you use ethylene diamine as a sample stabilizer, it forms a carbamate with carbonate, which can interfere with quantitation of fluoride. And we adjusted the selectivity to get essentially baseline resolution of those two peaks. And we also adjusted the selectivity of carbonate and sulfate peaks 6 and 7 so that they are well separated. On the S19, they are pretty close together. So that's the reason behind this new column. Then the AS31 is designed for separating haloacetic acids. Haloacetic acids are an important drinking water application. Haloacetic acids are often produced when you add chlorine to drinking water that contains some organic materials, and some of them are suspect carcinogens. The AS24 was originally designed for this purpose, but the analysis time is around an hour on this column, so one of the things that we wanted to do with the AS31 is speed up the analysis. Here you can see the comparison of the two columns with the same eluent condition. The AS31 is a little bit lower capacity, but not dramatically lower. It's just that the selectivity is quite a bit different. And you can see when we're analyzing haloacetic acids that the total analysis time is quite a bit faster. It's about, I think it was roughly 40% faster analysis time. This column is designed to be used in the ICMS mode. So we don't have baseline resolution of all the peaks, but all the peaks are that are important in the chromatogram are well resolved from the matrix ions. In the case of this column, we've designed it so carbonate and sulfate co-elute so that it simplifies the operation in the mass spec, because we want to divert the chloride and sulfate to waste when they elute so they don't clog the mass spec interface. Anyway, you can see that we have a much faster analysis with this column. Now, the AS32 column is a column that, frankly, we've been working on it for a long time. It's been available as a special product for almost 10 years, but it's a unique column that has extremely high degree of hydrophilicity. So ions that can't be eluted from any other column are easily eluted from this column. And this just shows you a standard test chromatogram. You notice there's no chloride in this chromatogram, and that's because it's not even baseline resolved from fluoride. But the purpose of this column is not to analyze common anions, but to analyze compounds like this. You can see a variety of different compounds ranging from toluene sulfonic acid to trisulfonates like naphthalene trisulfonate that on a normal column would never elute because of the hydrophobicity of the anion and the high charge. But on this column, we're able to elute all of these compounds. This column was originally developed with Eastman Kodak because a lot of those compounds are used in making, or at least they were used in making film. But it's also useful for compounds like polythionates and persulfate. And then a quick look at this new cation exchange column, the CS20. It was designed for operation in the gradient mode. So you can see here, we designed it with a big separation gap between monovalence and divalent ions, so there's room for separating many different amines. And here I'll show you a couple of examples. Here's a separation with all of the ethanolamines, mono-di and triethanolamine, as well as methyl diethanolamine and diisopropanolamine. So a range of different hydroxyl amines. And here's another separation with aliphatic amines, both methylamines and ethylamines, as well as piperidine. So this column is really specifically designed for use with analysis of amines. Now, the last column I want to show you is the carbohydrate column that's been around for a couple of years, designed for fast analysis of carbohydrates in foods. This is a separation of common sugars that are used in the test chromatogram. And you can see the analysis time is similar to columns like the Carbopac PA1. But we're able to resolve 20 different carbohydrates in less than 20 minutes with this phase, and able to resolve a number of carbohydrates that are difficult to resolve in other columns. And this is an example separation of several different honeys, and you can see the complexity of the carbohydrate profile in honeys. Everybody thinks of honey as being mostly fructose, but obviously it has many other sugars as well. So lastly, I want to talk a little bit about common problems with ion chromatography columns and possible solutions. I think the biggest problem I hear people talking about are peak-shaped problems. So the first question is, if you have a peak-shaped problem, is it all of the peaks in the chromatogram? If so, it's probably not a column problem, although it could be. It's more likely to be a plumbing problem on your instrument. So there, as I mentioned before, we recommend Viper fitting, so you don't have to worry about if you cut the tubing right or not. If you aren't using Viper fitting, make sure your fittings are properly cut and properly seated. Many times I've seen problems, and it was caused by a sample loop wasn't properly installed in the injection valve, and there's a little gap at the end that causes band broadening. So that's one thing to look at. Sometimes, if the frit is contaminated with particulate from samples, it can also cause peak-shaped problems. So when all else fails, open the column inlet and check whether or not the frit looks dirty. If it does, try replacing the frit. Now, if only one or two peaks have poor peak shape, it's probably some chemistry-related problem. It could be a variety of different chemistry problems, depending on what you're dealing with, but the most common one in my experience is metal contamination. If, for example, your sample has iron oxide, that can cause tailing of sulfate and phosphate. And even if you stop injecting samples, your column is contaminated with iron oxide, so you need to treat your column with oxalic acid to remove iron contamination. So try cleaning your column if you see bad peak shape for sulfate and phosphate, but the other peaks look relatively normal. Another problem that I hear about is resolution problems. The first question is your column performing normal, or has the column degraded? And the way to check that is to rerun the QC test on the column. If it's within 10% of the chromatogram that came with the column, it's probably your problem is probably sample related or related to some other parameter like your eluent choice or something like that. But if you see the retention time has decreased when you do that test, then you should try cleaning the column. What I recommend if you're going to clean the column is only do the test that you suspect would be relevant to your contamination. Like if you know that you've been injecting samples that contain metals, just do the metal cleaning test. Don't do the organic cleaning test. Or don't rinse the column with just acetonitrile. That's not going to help for a metal. Then the other question is the column overloaded? You know, if you're injecting too much, peak retention time or resolution can shift. Try injecting less. If you have matrix problems, like maybe the sample matrix, the pH is too high or too low, you may need to do sample prep. Sometimes the problem is caused by peak shape, in the suppressor, and that's particularly when I see that, it's usually polyvalent ions that you see that with. So if you see calcium and magnesium only or have bad peak shape for cations, you may want to try cleaning the suppressor by first exhausting it with the acid eluent and then regenerating it to see if the peak shape is restored. If retention time is drifting shorter, try cleaning the column. If the sample contains a polymeric anion or a polymeric cation, then you probably need to try to remove the contaminating ions before you inject them. Cleaning the column may help, but in some cases you may not be able to remove a sample of that type from the column, so it's better to remove it from the sample if you can. It's possible the column capacity is decreasing because of operating under outside of the recommended ranges. Like for most hydroxide columns, we recommend you don't use higher than 30 degrees unless absolutely necessary. So if you're using higher temperatures, try dropping the temperature down to 30. Another problem is that are a set of problems that are not column related but still worth thinking about. If the retention time is drifting longer, it can't be column related because column capacity can't go up, it can only go down. So that probably either means there's something wrong with your pump, or a problem I've seen myself is if you make up a batch of eluent and forget to mix it up well, then the concentration will be highest at the bottom of the bottle and lowest at the top, so the retention time will slowly drift up. If retention time is fluctuating, it's probably pump related, or it might be a degassing problem. Or in some cases, if the injection valve is a different pressure in the load and inject position, that can also cause the retention time to fluctuate. If the column life is shorter than normal, that really can't be column related because the column chemistry doesn't allow for the degradation of the column to change depending on batch, but it could be related to your samples, or it could be related to how you're using the column. Like I have seen cases where a customer is using a column under conditions where the column life is only 3 months, and sometimes in 3 months they inject 1,000 samples, and sometimes in 3 months they only inject 100 samples. Though if the column is only good for 3 months under those conditions, it doesn't matter how many samples you inject. The problem is the conditions, not the column. So consider whether or not you're operating outside the range of the column when you see that problem. And you might need sample prep if you are seeing if the column life is way too short. If the baseline is noisy, check for excess back pressure on the suppressor. Sometimes that will cause noise. Try degassing the eluent because sometimes the pump pressure stability isn't very good if the eluent isn't completely degassed. And sometimes you'll see pressure buildup in the suppressor that's caused by calcium and magnesium depositing in the suppressor. Just like an espresso machine, your suppressor needs to be cleaned periodically to remove calcium and magnesium. And the manual tells you how to do that. So I'm not going to explain that here. Now, last but not least, I want to talk about column storage conditions. The column life, all other things being equal, is dependent on the operating temperature, the eluent pH, and the stationary phase chemistry. Some chemistries, like the carbopac PA1, that chemistry is stable for years. In fact, I've seen data from the FDA showing tests on a carbopac PA1 over the course of 5 years with no measurable change in retention time. But there are other columns where if under standard operating conditions, they lose 1 or 2% of the retention per month. So if you have a column like that, you want to consider how you store the column when you're not using it. And then, so you really divide that into two categories because it takes more time to do proper storage. So if you're going to use it in a week, then probably it's easier just to leave the column in eluent and turn off the oven if your oven is at an elevated temperature. If it's convenient, you can reduce the pH of the eluent to 7 or rinse the column with deionized water. And remove any organic solvent from the mobile phase if there is any. For longer-term storage, we recommend one of two options. For cations, you don't really need to change the eluent. But for anions, we recommend storage in tetraborate eluent. Or if you have a refrigerator available, you can store the columns in eluent at 4 degrees for many months without any measurable change in capacity. And finally, in conclusion, I just want to say, obviously column selection is important for achieving optimal results in ion chromatography. If you haven't done so, try using virtual column. It's useful for developing new analytical methods and for picking the right column especially for samples that have unusual analytes. When you're selecting a column, consider the column capacity for concentrated samples. The high efficiency is important for complex samples, and short columns are best for less complex samples. And then I talked about all of these columns. I'm not going to review that here. And then the last thing is that we really do recommend that you put your column in a storage solution when you're not using it, especially if you're not going to use it for more than a week. All right, so.
Thank you, Chris. And here you go. You can see the results of the top 3 challenges that laboratory professionals faced in their laboratories for IC, which the top challenge is reproducibility and robustness. The second challenge is productivity, and the third challenge is sensitivity. So I'm going to hand it over to Christopher, who will be able to explain how you address these top 3 challenges for ion chromatography columns. Thank you, Chris.
Okay. So I'm going to briefly review, different approaches. Some of these are repeat of what you just heard. But first and foremost, if you want to maximize your reproducibility and robustness, the first thing is to make sure your column is fully equilibrated before you start a sequence. And it depends on what your reproducibility requirements are. But if you need better than 1% RSDs on your analytical data, you probably need at least an hour of equilibration before you start. Otherwise, your first few runs won't be in line with the rest of them. in Chromeleon, there is an option to have a startup method that starts automatically before you get to work in the morning. So you can program your setup so that it's equilibrated when you arrive in the lab. Another thing is, for gradient methods, make sure your re-equilibration time is sufficient. If it's marginal, then it's going to matter what the frequency of injection time is. And with autosamplers, depending on the design, the time it takes to make an injection isn't always constant. If your equilibration isn't sufficient, you'll have some variation due to fluctuations in the exact cycle time from one injection to the next. Another thing I recommend is to operate your autosampler in the sequential mode if it has that mode. If you use a simultaneous mode, when it just so happens that both samples need to be injected at the same time, one will have to wait until the other one is done, and that will affect reproducibility. Use high-capacity columns. They invariably give better reproducibility and robustness. Use fixed-loop injection. It's not dramatically more reproducible, but it usually gives you at least a little bit better reproducibility than using partial loop injection. Use isocratic conditions if you can, because they're always more reproducible. Don't overload your column, and only use the recommended suppressor current. A lot of people think you should use a higher current than the recommended current, and in some cases you need to do that, but often that affects noise and therefore reproducibility. Now, when it comes to shorter analysis time, I did talk a bit about this before. With simple samples, you want to reduce the analysis time by just using a shorter column. For more complicated samples, if you use a smaller particle size columns, then you can use a faster analysis time without reducing the length by just speeding up the gradient, for example. Another option, obviously, is to increase the flow rate. Raising the flow rate, of course, means your eluent doesn't last as long and it consumes more reagents, but it invariably improves your speed. One thing to remember if you want to do shorter analysis time is to make sure your system dead volume is as small as possible. And we also recommend you use Viper fittings in that case, because when you're using shorter columns, it's more important that you don't have any dead volume in your system. And Viper fittings guarantee that you don't have that problem. And then finally, for sensitivity, as I said before, if you use smaller particle size columns, you'll have higher efficiency, which means taller peaks. Shorter columns will also produce taller peaks. If you operate your suppressor in the external water mode or the chemical mode, that will reduce noise and therefore improve your detection limit. You want to make sure your cell back pressure is in the proper range, because too much or too little back pressure can increase noise. And as I mentioned before, only use the recommended suppressor current.